Hi everyone, my name is Nikhil, Assistant Professor, Department of Mechanical Engineering, Jyoti Engineering College. Now we can study the expression for crippling load when both the ends of the column are fixed using Euler's column theory. Now consider a column AB of length L and uniform cross-sectional area A fixed at end A and B. So in this figure you can see the column A and B, and the total span of this column is represented as capital L, and both the ends, that means end A and B, are fixed. Now P is the crippling load at which the column just buckled. So you can see at both the ends A and B the load P is acting. Due to crippling load, the column will deflect into a curved form ACB. So initially the column was perfectly vertical, but after the application of load P, it will deflect into a curved form, that is ACB. Due to fixed ends, there will be fixed end moments, say M0 at the ends A and B. Since both the ends of the columns are fixed, definitely there develops fixed end moments. It is represented as M0. Now we can consider any section at a distance x from end A and let y equal to the deflection or lateral displacement at the section. So from end A you can see the distance x is marked, and at that point the lateral displacement or deflection is represented by y. Now the moment due to crippling load at section equal to M0 minus P into y. So the total moment, which is equal to, here we are taking clockwise moment as positive and anti-clockwise moment as negative. So with respect to point B, two moments are acting. The first one is M0, that is the fixed end moment, so that you can see here, and the second one is the moment due to the force P acting at point B. That moment is moment equal to, as we know, moment equal to force into perpendicular distance. So this is the line of action of the force P, and this much is the perpendicular distance, and this force will make an anti-clockwise moment. That is why we put a negative sign. So the total or the moment due to the crippling load at the section we have selected, which is equal to M0 minus Py. But we have another equation for moment, which is equal to EI into d square y by dx square. So we got two expressions for moments. Now equating two moments, we will get EI d square y by dx square equal to M0 minus Py. Now rearranging the equation, you will get EI d square y by dx square plus Py, which is equal to M0. All these steps are quite similar that we done in the case of columns with its both ends are hinged. The only difference, the main difference coming in the case of a moment due to the crippling load. Rest of the things or the steps are almost similar. Now this equation we can written as d square. That means dividing this equation by EI, you will get d square y by dx square plus P by EI into y, which is equal to M0 divided by EI. Now this equation can be written as d square y by dx square plus alpha square y equal to M0 divided by EI. this is taken as equation number A, where alpha square equal to P by EI, or alpha equal to under root P over EI. Now, the solution of the above equation is y equal to C1 cos of alpha x plus C2 sine of alpha x plus m0 divided by EI alpha square. Therefore, substituting the value of alpha, that is alpha equal to under root P upon EI in this equation, you will get y equal to C1 cos of x into under root P upon EI plus C2 into sine of x into under root P upon EI plus m0 divided by E into I into P by EI, which is equal to y equal to C1 cos of x into under root P by EI plus C2 into sine of x into under root P by EI plus m0 divided by P. That is taken as equation number 1. Now we have two end conditions, that is at end A and end B. Now here at A, x equal to 0, y equal to 0, and also the slope, that is dy by dx, equal to 0. Similarly, as B is fixed at point B, x equal to L, as I said earlier, from this point to the point B, or moving from point A to point B, the value of x is increasing from 0 to L, and when reaches at point B, the value of y equal to 0. So at point B, x equal to L, y equal to 0, and also the slope, that is dy by dx, equal to 0. Now applying the end condition in equation number 1, that is substituting the values that is x equal to 0 and y equal to 0 in equation number 1, you will get 0 equal to C1 cos 0 plus C2 sin 0 plus m0 by P, and solving that equation, finally you will get C1 equal to minus m0 by P. That is taken as equation number 2. Now we have y equal to C1 cos of x into under root P upon EI plus C2 into sine of x into under root P upon EI plus m0 by P is taken as equation number 1. And differentiating the equation and substituting the values x equal to 0 and dy by dx equal to 0 in that equation, you will finally get the expression or the equation 0 equal to C2 into under root P upon EI. From that equation, either C2 equal to 0 or under root P upon EI equal to 0, but for crippling load P, the value of under root P upon EI cannot be equal to 0, therefore C2 equal to 0. Now substituting C1 equal to minus m0 by P and C2 equal to 0 in equation number 1, we get y equal to minus m0 by P cos of x into under root P upon EI plus m0 by p, that is taken as equation number 3. Now we can take the other end condition, that means at end condition at point B. At the end B of the column, x equal to L and y equal to 0. Substituting these values in equation number 3, we get 0 equal to minus m0 by p cos of L into under root p by ei plus m0 by p. And solving that equation, you will get cos of L into under root p by ei equal to m0 by p into p by m0, which is equal to 1. So that condition is satisfied only if the value for L into under root p by ei equal to either 0 or 2 pi or 4 pi or 6 pi, like that. Now taking the least practical value, you will get, or we will get the expression L into under root p upon ei equal to 2 pi. Now squaring both sides, the equation changes to L square into p by ei equal to 4 pi square. Now rearranging the equation, you will get the expression for the crippling load P, that is P equal to 4 pi square ei divided by L square. So this is the final expression for crippling load if both the ends of the column are fixed. This expression is also very important in the examination point of view. Hope you understand the derivation of this expression, and you can expect some problems from this topic. Now these are the two expressions for crippling load for different end conditions we have studied. In the case of both ends hinged, the relationship between effective length and actual length is LE equal to L, and corresponding to that end condition, the expression for crippling load in terms of effective length equal to pi square ei divided by LE square, and in terms of actual length is P equal to pi square ei divided by L square. And in the case of both and fixed, the relationship between effective length and actual length is LE equal to L by 2. And the expression for crippling load in terms of effective length is P equal to pi square ei divided by LE square, and in terms of actual length is P equal to 4 pi square ei divided by L square. So you must thorough with these expressions. Thank you.